So we're going to be going over linear algebra this week, and there's a few different topics and subtopics. We'll talk about matrices first and go over some basic revision from first year math courses, but also some more advanced stuff. And then we'll go a bit deeper into span and independence and some problems around that. And then we'll talk about eigenvalues, eigenvectors, solving problems related to those, and we'll go over 2 different linear algebra theorems that you may or may not have seen before.
Okay, so first we'll go over linear mappings. So a mapping transformation from V to W between vector spaces that share the same field is called linear when these 2 properties satisfy. So the first property is transformation of vector U plus vector V is equal to the transformation of U plus the transformation of V. So this is called the vector addition property that we have to satisfy for a transformation to be called linear. The second property is the scalar multiplication property, which is the transformation of a scalar A times vector V is equal to that scalar A times the transformation of vector V. And alternatively, we can combine those 2 properties into just a single thing that we have to satisfy, which is the transformation of A times vector U plus B times vector V is equal to the A times the transformation of U plus B times the transformation of V. So instead of proving 2 properties, now we only have to prove 1. And we can clearly see that this property involves the scalar multiplication, which is A times transformation of U, and the vector addition, which is adding those 2 terms together. And we'll see that property in use in our next example. Can we go to the next example? Yep, so this example, we have to show that the derivative is a linear mapping from the set of infinitely differentiable functions C to itself. So maybe we'll give you guys a minute or 2 to think about how you guys can approach this question. So obviously we have to start, and we have to try to use our property that we just demonstrated before. Also, if you have any questions about what I just said, feel free to ask in the chat. Yeah, so like what Odin pointed out, you should approach this question from the first definition of derivative. So the limits x plus h definition. Yep, so the limit when h approaches 0 of this formula is the derivative of a times fx plus b times gx, right? And we can separate this function, we can separate this into a times the limit when h approaches 0 of the function in f, and b times the limit when h approaches 0 of function in g, I believe, not f. So this should be g of x plus h minus g of x, which then we can just simplify into a times the derivative of f of x plus b times the derivative of g of x. And I guess a thing that's worth pointing out is that the linearity of the derivative, which is this one, which is equal to that, is a consequence of the linearity of the limits, which is where we separated this entire limit into the two smaller limits. Okay. Does anyone have any questions on that? If not, we can move on to our next point, which is the matrix representation theorem. So if a vector space has a basis E1, E2, those are just the unit vectors with 1 in one of the directions and 0 in all the other directions. We can write any vector as a linear combination of these vectors. So just to clarify on basis, another property that they have to satisfy is that they have to be linearly independent from each other. So obviously that is the case since these are the standard bases. So this implies that the transformation of vector v is equal to the transformation of a1 e1 plus a1 a2 e2, etc. So because those are bases for that vector space, we can express vector v, which is in that vector space, into those constituent bases. And from our linear mapping theorem from the last slide, we can then separate it into the scalar a1 times transformation of e1 plus a2 times transformation of e2, etc. for the collections of scalars a1, a2, and so on. So we then let EI, which is one of the bases, be equal to the transformation of EI. Then this matrix product, so that would just be, so all of these are columns, individual columns, and we multiply this matrix product and we get the coordinates of transformation of V. So can we get one more line? I think that explains it. Is that the correct PowerPoint? Because I believe there was another version that I was seeing before.
Might have been this one.
Sorry guys, just bear with us for a minute. Oh no, this is just with extra examples. So I can also explain this. So it's fine, I'll just explain this one. So basically concluding what I just said, for every vector space with a basis, so for example, the span of sin x and cos x, a linear mapping from that vector space to itself can be represented as a matrix with dimension equal to that of the vector spaces. That is basically, so what this means is basically this matrix product. Okay, and matrix multiplication in general is defined as, so the column ij of the product of AB is equal to this expression, which will be seen in more details in the next slide. Does anyone have any more questions about this? If not, I'll pass it on to Yasuru for the next example.
All right, so next example, we will look at some applications of using matrices. So you might ask, why do we even care about using these matrices? So let's have a look at this example question. So looking at the population of rabbits and how they increase each month. So let's say in month n, Fn is the population of the rabbits, and let's also say initially in month 1 the population is 1, and month 2 the population is 1. So that's the starting population. That's the populations in first 2 months. But then the populations explode rapidly, and the rule for how the population increases is the population f of n plus 2. So in month n plus 2, the population is equal to the population in month n plus 1 plus population in month n. So it's a recursive formula where the population in the next month is determined by the population in the previous 2 months. And I think most of you will recognize this well-known formula as the Fibonacci sequence. So it goes like 1, 1, 2, 3, 5, 8, 13, and so on. So what we have to prove is this interesting identity. So this identity holds for all positive integers m and n, which is f of m plus n plus 1 is equal to f of m plus 1, f of n plus 1, plus f of m, f of n. That's quite an interesting identity. And believe it or not, matrices come into this. So let's have a look at this interesting matrix 1, 1, 1, 0. So it's quite a simple looking 2 by 2 matrix, but a lot of powerful things can be achieved using this simple matrix. Okay, so let's go to the next dot point. All right, so what happens when we multiply these matrices M together? Okay, let's say let's use annotation. We have a look at this entry and this entry. We have 1 and 0. What we can also do here is just define f of 0 to be 0. So that's it's a starting value for Fibonacci sequence. And we have f of 2 equals f of 1 plus f of 0. So the recurrence still works when you include the 0. So what I can see is this is equal to f of 1. This is equal to f of 0. this is equal to f of 1. This is equal to f of 2. And what would happen if we find what m squared is? We calculate m squared. You'll get 2, 1, 2, 1, 1, 0. Wait, 2, 1, 1, 1. And if you do m cubed, so one more example. We get 3, 2, 2, 1. So an interesting thing is if you keep on continuing finding the powers of m, you actually get all the Fibonacci numbers in your 2x2 matrix. That is quite an interesting observation. And it turns out that you can prove by induction that m to the power of n gives you these 4 Fibonacci numbers in terms of n. And so you can have a go at trying the inductive proof yourself as an exercise. So quick way of doing this inductive proof is, a quick outline is if you write m to the n as m times m to the n minus 1, you can sub m here, and using the inductive hypothesis, you can sub in m to the n minus 1 here. And then using this identity, using this recurrence over here, and also using the fact that the base case works, you can prove this identity for m to the power of n. Okay, so if we go to the next dot point, we'll see. So another interesting fact is that matrix multiplication is associative. So A times BC equals AB times C. So no matter what matrices ABC are, if it's possible to multiply them, it doesn't matter how you put the brackets around ABC. So this is also a nice, if you haven't seen the proof of this before, it's also quite a nice exercise to prove. So what it means is the brackets don't matter when you multiply matrices. So you can just write ABC here, and there's a unambiguous definition for how the multiplication works, because you get the same answer no matter where you put the brackets. So you can use the fact that it's associative and group the brackets in a specific way. So m to the power of m plus n is the same as multiplying m by itself, m plus n times. And we can also group the brackets like this. So you have m times m dot 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 m times, and m times m dot 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 n times. Okay. And now using the previous identity here, you can sub in this m to the power of m is equal to this, and m to the power of n is equal to this. And also remember that m to the power of m plus n is the same as the left-hand side using the previous identity. So it means you're using this identity and you're evaluating m to the power of m plus n in a specific way. And this specific way of breaking it down is like this. And now we have this matrix, these two matrices. And so the left-hand side and right-hand side is supposed to be equal, but it doesn't seem immediately obvious why they are equal. We kind of use an indirect means to prove left-hand side and right-hand side are equal using this associativity fact. But a nice consequence of this associativity fact is if you expand the right-hand side, so we can go to the next. Let's see. Okay, now expanding out the right-hand side, you can look at the top left entry over here, and this is used to find the top left entry. And if we evaluate the top left entry on the right-hand side, we'll get this right-hand side here, and this left-hand side here matches this top left entry. So it's completely out of the blue. Somehow, just manipulating matrices has helped us prove our desired identity for size of the rabbit population. So that was quite a spectacular application of matrices. Okay, so anything after this, I can't remember.
Great, thanks, Yasiru.
I think that's it. Yeah.
Yeah, I think if you are feeling like this is a bit out of the blue, it's worth noticing that if we're going to repeat a linear transformation like this, it has to be a square matrix. You can't take higher powers of rectangular matrices, so it's going to be n by n. And if you think about the Fibonacci sequence, you'll see that each term depends on the previous two terms. So in some sense, you need two different numbers to keep track of where you are in the sequence. And I think it's worth, maybe after this workshop, having a bit of a think about how this matrix can be interpreted in terms of this sequence here. So we'll move on to determinants, and the usual motivation for determinants is their higher order. So if you think about where the basis vectors go under a transformation that's represented by a matrix A, they're going to form some kind of rectangle or rhombus or higher dimensional parallelepiped shape. And the determinant is just the scaling factor of that shape. Because if you think about the cube whose edges are the basis vectors, the canonical basis vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. That cube has area 1. After you transform that cube under the linear transformation, it's going to have a new area. And sometimes sometimes the volume will be 0. And that's when you get squished down into a plane or a line or even a point if it's the 0 matrix. And that tells you something also about invertibility. So the computational definition of the derivative it's a bit strange. But basically, if you want to evaluate the derivative for any matrix, the way you do it is recursively. So you have to go along the top row, and you look at this A here. You take the matrix A, first row, the ith entry, so the first entry. And then we have this -1 to the I plus 1. So the first entry plus 1, so that's 2, -1 to the 2, so it's just positive. So we're going to take A, and we're going to multiply it by the determinant of the matrix A without the entries of the form 1 something. So without the first row, and also without the entries of the form something I. So I in this case is 1. So we're going to remove the first row and the ith column, and we'll add that to our sum. And we'll do that for every element, every column, every element in the first row. And this takes our 3 by 3 matrix down to a sum of 2 by 2 matrices. And if you have any n by n matrix, you can find the determinant just by doing this. And if you want to find the determinant of a 2 by 2 matrix, that's just the first element times the rest of the matrix, so E times I, minus the second element times the rest of the matrix, so EI minus FH. And as we said before, the reason you might care about determinants is for determining invertibility. So here's an interesting determinant problem. So we have these powers of different numbers going up along the matrix. And we want to ask what is the determinant of this matrix, which is known as the van der Waals matrix of order n. And if you focus on this xn term over here, and you think about our formula for the determinant, we're going to go along here. We're going to take this first entry here times the determinant of this section of the matrix. And then we're going to subtract this element here minus the determinant of the rest of the matrix without this column and without the first row. And we're going to continue along adding and subtracting like that. And what we're going to end up with, we're going to end up with a polynomial expression in all of these. But in this case, we're going to interpret that polynomial expression as having xn as the variable, and we'll treat these as constants in some sense. And we can see that the degree of this polynomial should be n minus 1 with respect to the variable xn. And we can also ask, what are the roots of this polynomial? Well, the roots of this polynomial are going to be all of these entries over here. The reason for this, you think about this xn term over here. That's a very good question. So if we apply our recursive formula, we'll have a whole lot of additions and subtractions here. And if any of these x1, x2, x3, and so on are equal to xn, we're going to end up with a cancellation as we go along and add, subtract along the top row. And then when we're calculating the lower order determinants. So if x1, for example, is equal to xn, well, we're going to take this first term here times the determinant of this bit. But that's going to be subtracted when we come along here and take this term times the determinant of this bit. And the reason it's going to be subtracted is because we're saying that x1 is equal to xn. And for all these ones in between, when we evaluate these, the matrices that we get without one of the columns, half of them are going to have a positive sign and have x1, and half of them are going to have a negative sign and have xn. So if any two of these numbers, if any of these numbers is equal to xn, the whole thing is going to end up being 0 if we go and expand recursively. So we can see that the roots of this n-1 degree polynomial have to be these ones here. And because there's n-1 of those different numbers, we know that's all of the roots. So now we want to ask, what is the leading term of this polynomial? And the leading term of this polynomial, once we're saying that these can't be xn, well, the leading coefficient is going to be just this xn to the n-1 term without any of these lower order terms, because we just care about the leading coefficient. So it's going to be this xn to the n-1 term, possibly minus, possibly plus, depending on whether there's an odd or even number of terms in the top row. So we're going to take this term, some sign, and the rest of the matrix, the determinant of the rest of the matrix, is going to be the leading coefficient of the x to the n-1 term. So in other words, the determinant of this nth order van der Waals matrix is going to be plus or minus the determinant of a smaller van der Waals matrix, which is this section of the matrix here. That's going to be the leading term. And if we multiply the leading term by all of the roots, so all of the linear factors that are monic linear factors, monic polynomials, this will have to multiply out to the determinant of the whole matrix here. And if we repeat this recursively, we're writing this determinant of van der Waals order n in terms of the determinant of van der Waals order n-1. And if you expand this out, you're going to have xn minus x1 as a factor, xn minus x2, and so on up to xn minus xn minus 1. And then in here, you're going to have xn minus 1 minus x1, also minus x2, also minus x3, and so on. So this polynomial argument, in terms of the determinant expansion, shows us that this determinant has to be this very simple product of all the factors where the first index is bigger than the second index. And so even though these are just arbitrary numbers, there's a very nice expansion for the determinant in terms of these arbitrary numbers, because we have this nice pattern going up of the powers, and we can make this polynomial argument about them. So we'll move on to talking about matrix inverses. Let me know if there's any questions about that previous question. I don't want to rush things, but I'll move on for now. So obviously what a matrix inverse is, if you multiply a matrix by its inverse, you get the identity matrix. And the identity matrix, if you multiply anything by the identity matrix, you get the matrix you started with. So hopefully we're familiar with that. We'll go over an example problem. If we have a symmetric matrix, that is, if you flip along its diagonal, you get back the same matrix. So it's symmetric along the diagonal, and it has positive real entries. And it's at least a 2 by 2 matrix. It's not just a 1 by 1 matrix. We want to say something about the number of entries in the inverse that are equal to 0. And so one way to think about this is, let's just use the formula for matrix multiplication, because we know that this product, A inverse, is just the identity matrix. So we'll write on the left-hand side just the definition of each ij entry in that product. And here, this delta ij is just saying, if I and j are the same, delta ij is 1. If I and j are different, delta ij is 0. So this over here is really telling us what is the ij entry of the n by n identity matrix. And because we know that A is a positive matrix, if you think about A inverse, for each value of j, so for each column in the identity matrix, we have to have some value where it's 1, and some value of I where this is 1, and some value of I where this sum is 0. And because of that, we know that one of these entries for some I, all of these are going to be positive. So in a inverse, we're looking at column J. Well, if column J is all zeros, we're only multiplying by column J. So all of these for any value of J will be 0, but we can't have that because in the jth column of the identity matrix in the ith row and the ith column, the jth column in the ith row, there has to be some value in each row of the identity matrix that is 1, and some value in each column of the identity matrix that is also 1. So this can't be all 0, but it also can't be all positive, because if it were all positive, then every delta ij would be positive and we wouldn't get any zeros here. So we have to have some cancellation in this sum to get zeros, since all of these are positive. And if we follow this argument through, we end up seeing that A inverse has to have at least one positive entry in this column, in this row, sorry, in the ith row, and at least one negative entry in the ith row, which means it has 2 entries not equal to 0. And if every row has 2 entries not equal to 0, well, we know that there are 2n entries in the matrix that are not equal to 0 because there's n different rows. And if we think about the total number of entries in the matrix, it's going to be n squared because it's an n by n matrix. So if we have 2n non-zero entries and n squared total entries, then we have at most n squared minus 2n entries which are equal to 0, because we have to have at least 2n entries which are not equal to 0. So hopefully that is all clear. We'll move on to talking about independence now, and we'll go over some concepts like rank, and then we'll move on to eigenvalues, eigenvectors, and then some theorems. Cool. So I want to talk a little bit about a generalization of what we mean when we say that a set of vectors is independent. So if we take an arbitrary set V, V has a bunch of subsets, and some of these subsets, we're going to call them the independent subsets, and we're going to have to have this setup satisfy a few different properties. And this kind of approach of taking a bunch of subsets of a set and requiring them to have some relations to each other, it comes up when defining other kinds of objects in mathematics quite a bit. If you take a course on formal topology, for example, often a topology will be defined in terms of taking some subsets of a set and requiring them to satisfy a few different axioms. So we can generalize this notion of vector independence to a more generic notion of subset independence. And obviously, if you have an empty set of vectors, you're not going to have 2 vectors in that set be dependent on each other, because there's no vectors in the set. And if you have a set of independent vectors, you can certainly remove any of them, and you're not going to create a dependence by removing any of them. And we also we have this idea of the dimension of a vector space. And there's this sense that, well, if we have an independent set, it can be at most, the biggest it can be is the dimension of the vector space. And there's kind of, in an n-dimensional vector space, there's n different directions that you can go in. And so we also require this exchange property. And what we mean by the exchange property is we have this big set of independent vectors and this smaller set of independent vectors. Well, because there's some number n of different directions in the vector space. Well, B has less than n directions, certainly because it's smaller than A. And so if B has less than n, it's pointing in less than n different directions. Well, there must be something in A that contains a new dimension that's independent to the rest of them. And so this generalization of independence is something called a matroid. And there's a lot of nice examples of matroids that aren't vector spaces. One example you might want to think about after the workshop is if you have a graph with some edges. Well, if you take a subset of those edges such that there are no cycles in the subset, and what we mean by a cycle is kind of a loop in the graph like this. If you take all the subsets of edges where the edges don't form a cycle, well, along with the graph, that's an example of a matroid setup. So there's no vectors here, but there's still some shared properties with ordinary vector spaces. So continuing the discussion about dimension, if you have a matrix, well, you can ask about the dimension of the set of rows of the matrix and the dimension of the set of columns of the matrix. And so there's only a certain number of ways you can combine, there's only a certain number of directions you can get by combining the rows of the matrix. And there's only a certain number of directions you can get by combining the columns of the matrix. And in fact, it turns out that the number of different directions you can point in by combining rows or by combining columns is going to be the same, whether you're looking at the rows or the columns. And one heuristic argument for this might be to consider invertible matrices only. And invertible matrices, well, if you have a non-invertible matrix, often you can kind of nudge some of the entries a little bit. You can add a small constant to some of the entries and turn it into an invertible matrix. So this is, it's not a formal argument, but by just considering invertible matrices, it's kind of a heuristic argument for why this is true in general. And if we take an invertible matrix and reduce it to reduced row echelon form, we're going to be able to make it have zeros everywhere that's not the diagonal. And because of this, well, if you think about the span of the rows of the matrix, you kind of have one free direction here, one free direction here. If you're taking a linear combination of these, you can get really any vector by combining rows that has some entry in the first column, some entry in the second column, and so on, all the way along the diagonal. So if there are n elements in the diagonal, well, you can get an n-dimensional subspace by combining rows, but also just symmetrically by combining columns. The subspace you get is also n-directional or n-dimensional. So that's a rough argument why that's the case. And one way you might want to apply this is, okay, well, so in this question where we're looking at this special subset of R to the n where the coordinates are 0 or 1, and Z is not a subspace, because certainly if you add vectors whose coordinates are 1 together, you won't necessarily get vectors whose coordinates are 0 or 1. But if we do take a subspace of R to the n, and we want to consider sets that are both, we want to consider vectors of this form that are also in the subspace, well, we want to ask how many, supposing this subspace is of dimension k and the broader space is of dimension n, well, how many points, how many vectors of this form can we get that are both of this form and in the subspace? So they're in the intersection of these two sets. So we can put these in a matrix, all these different elements in the set. And because this subspace is k-dimensional, obviously the span of the elements of the intersection, the span of those is going to be at most k-dimensional. And because we have this equality between the rank of the rows and the rank of the columns, we can pick a set of k different columns which spans the column space because the column space is most k-dimensional. So if we had to choose k+1 columns, then it would be k+1 dimensional. But because it's just k-dimensional, we can do it with only k of the columns. So if you think about each row, if you know the coordinates in, so we have some matrix. So we have entries here. Because we're picking these first k columns to be a set, not necessarily a basis, but a set that spans our column space, we'll say they're the first k columns. Well, if we know these first k columns, because the rest of the columns are a linear combination of these first k columns, well, if we know these first k, which have to be 0 or 1 because they're in the intersection, then we know the rest of them. So we only have to pay attention to these first k. And for each of these, there's two choices, 0 or 1. So the number of rows, the number of choices for each row, because the rest of the positions are determined by these first k, is just 2 to the k. So there's certainly not more than 2 to the k rows by that argument. We want to find the maximum possible number of points. So we also have to find an example that has 2k rows. And so if we simply make V have, if we take all the possible vectors of this form and we take their span to be V, this form meaning we have arbitrary entries in the first k spaces of the vector, and the rest are just some linear combination of those first few. There's 2 to the k of those. We can put those as the rows of our matrix as the elements of this intersection. And the span of that set of vectors is what we will call our V. And because by construction there are 2 to the k vectors in this spanning set of V, and they're all of this form, well, certainly the intersection is going to contain 2 to the k and no more because it's at most 2 to the k. So we'll try another question that's related to independence. So we have this setup where we have this special matrix X and this initial matrix B0. And we're going to define this recursion here, which is the previous matrix times X minus X times the previous matrix. And of course, matrices are not commutative. So this isn't necessarily 0 in every instance. But we're going to make the argument that if we have this special property that doing this n squared times gets you back to X, well, then we're going to say that can't happen unless X is the 0 matrix. So let's take this Bn squared matrix and ask, well, what comes next after it in this sequence? And just by definition, we can expand it like this. And because Bn squared is X in this special case, we do actually have it commute because Bi minus 1 is simply X, and X commutes with itself. So in this case, we do get the 0 matrix. And because we get the 0 matrix here, every matrix after Bn squared plus 1 in this sequence is also the 0 matrix. Because we simply have 0 times X minus X times 0. And we're going to use the fact that the set of n by n matrices is actually a vector space, an n squared dimensional vector space. We're going to use this to make a dependence argument, a linear dependence argument, to show that, well, if this property holds, then because we can see that every matrix after this is also 0, this X here has to be 0. So because there are n squared entries in an n by n matrix, we can have at most, the dimension can be at most n squared. And in general, for n by n matrices in R to the n, the dimension is n squared. But here, if we look at the matrices from B0 up to Bn squared, there's more than n squared matrices here. And in this case, we'll interpret them as elements of a vector space. So we'll actually call these matrices vectors in the formal sense of obeying the vector space axioms. And since there's more than the dimension, since there's more than n squared vectors in this collection, they must be linearly dependent in some sense. So we can see that there's some linear combination of them that's the 0 vector, or in this case, the 0 matrix. And not all of these are 0. So we'll pick the first one of these where the coefficient isn't 0. And we'll move it over to the other side. So we can write this non-zero scalar times the matrix times minus 1 as a linear combination of the rest of them. And so now what we're going to do is we're going to apply this recurrence here to this setup, noticing that we can kind of ignore this and just ask, well, what's Bk plus 1? And we'll say Bk plus 1 is this whole thing with this transformation applied to it. So the coefficient times Bk minus 1 is, well, it's going to be minus ck, so this constant, and then just the definition of the recursion. And if we expand this out, given this linear representation in terms of the other matrices, well, we end up with all of these times x on the right minus the same set with x on the left. But if we go in the other direction, well, we can see that we have something times x here minus x times the same something over here, which is of this form. So we can collapse this a little bit and see that, well, this constant times bk plus 1 is this other expression in terms of another set of matrices. And if we continue this by induction, eventually we'll reach the case where we'll go from bk to bk plus 1 to bk plus j. And we'll add j to all of the indices on this side. And so now if we look at this case, where k plus j, it goes all the way up to n squared. Well, now what we see is, if we plug in x here, because we derived this property earlier that bn squared plus 1 is 0 and all the ones after it are 0, if we keep increasing these indices, we're going to eventually get to a whole bunch of 0 matrices. So we're saying some constant times x is a linear combination of a bunch of 0 matrices, which is just the 0 matrix. And because this constant is not 0, that implies that x is the 0 matrix. So we've made use of the fact that matrices form a vector space, an n squared dimensional vector space, to talk about linear dependence of matrices. And that's allowed us to combine that with what we know about matrix multiplication and what we know about this special recursion here, to argue that x is the 0 matrix. So now we'll look at eigenvalues and eigenvectors. And in case you've forgotten or you're not familiar with it, the idea behind eigenvalues and eigenvectors is when you multiply vectors in a space by a matrix, sometimes you'll have it such that there are particular vectors where multiplying them by the matrix is the same as multiplying them by a scalar. In other words, they stay pointing in the same direction, but they might get twice as long or half as long, or go negative and flip around. But they're still in the same line through the origin. And we call vectors like this eigenvectors. Eigen means own in German, I think, because they maintain their direction. And this scaling constant, which sometimes we say that the vectors are complex entry vectors and the scaling constant is a complex number. We say that the scaling constant is an eigenvalue of the matrix. And one of the good reasons for taking this to be a complex number is, well, if we try to find the eigenvalues, we might rearrange this to bring a times the vector over here. And in that case, well, if we take this vector, if we're saying that 0 is lambda times the vector minus a times the vector. And in this case, this is the 0 vector. Well, we might move this vector out and say that this is lambda minus a times the vector. And we can't really subtract a matrix from a scalar. But what we can do is say that this is lambda times the identity matrix. And the reason we want this to be 0 is we're asking, well, for which values of lambda do we lose a dimension? Which values of lambda does this this matrix difference squish our vector space into a lower dimension? And the reason for looking at that is, of course, because we want to find examples of values for which there's a scaling by some constant. And if this is an eigenvalue, then this matrix difference will have the effect of losing a dimension when we multiply our vector space by it, which is the same as saying that the determinant is 0. And this is going to turn out to be a polynomial, which is the reason we want lambda to be a complex number, because if we want to find the eigenvalues of this matrix, we have to solve this polynomial. And the polynomial is always going to have solutions if we make our domain be the complex numbers. Sorry, this should be lambda in C, not lambda in C to the n. And when this characteristic polynomial has roots in multiplicity 1, that is, it doesn't have any quadratic factors. Well, then, in that case, we can actually use this set of eigenvectors, which we say each of the eigenvectors has multiplicity 1. We can use this set of eigenvectors as a new basis in which to write our matrix. And because of this nice scaling property, the matrix in the new basis is actually going to be a diagonal matrix. So we can change our basis into the eigenbasis, represent this matrix as a diagonal matrix, and then change back out again to get back A in the canonical basis. And one reason you might want to do this is if you take power of this product, a higher power, you're going to have B, D, B inverse times B, D, B inverse, and so on. And the B's and B inverses are going to cancel. So you'll just have B times D to a power times B to the minus 1. And D to a power, because it's a diagonal matrix, you can just take the entries to that power. So it makes it easier to evaluate higher powers when you find an eigenbasis. So we'll look at a question that involves properties of the set of eigenvalues. So we want to say that V is some kind of subspace of R to the M, and W is a subspace of R to the N. And we're going to apply the matrix representation theorem here and say that A and B are just matrices rather than linear maps, because that's easier to talk about. And so really what we're saying is if they have the same set of non-zero eigenvalues, well, lambda is our variable in characteristic equation. And we want this to be 0 precisely at the eigenvalues for eigenvalues of AB. And we want this to be 0 at the eigenvalues for eigenvalues of BA. And this constant is just to account for the difference in the dimensions. So now that we've reduced our claim about these having the same set of eigenvalues, non-zero eigenvalues, they have the same set of non-zero eigenvalues if this equation holds. And now we're going to reproduce this equation further. If we just take this one to be the bigger one, then, well, if A and B are rectangular matrices, well, it'd be nice if they were square. So we'll just add a whole bunch of zeros to the shorter dimension, to the shorter direction of the matrix to make them square. So if we have, for example, 1, 1, 3, 2, 4, 5, this is a rectangular matrix. We'll just add some zeros here to make it square. So now that we have two square matrices, the determinant of this equation in terms of the transformed matrices is the same as this determinant here. And we also have this for the opposite case, where we're talking about BA and we're transforming them by adding a bunch of zeros. And so because of that, this equation here, by adding these zeros, we've simply reduced it to this property, which is true in general of n by n matrices, that swapping this difference here, when you subtract it from some scalar times the identity matrix, it doesn't actually matter which order you evaluate this in, the determinant is going to be the same. And because that's true in general for n by n matrices, this equation here has to hold, which means that AB and BA have the same set of non-zero eigenvalues counted with multiplicity. So now we'll go over two different theorems relating to linear algebra. The first one is the spectral mapping theorem, and the second one is the Cayley-Hamilton theorem, which is very nice. But first of all, so in physics, it's common to call the set of eigenvectors a spectrum, in a similar sense to how you talk about an electromagnetic spectrum or a light spectrum. And so the spectral mapping theorem is related to what happens when you evaluate a polynomial on a matrix. So obviously, if you have a square matrix, you can take a squared, a cubed, because you can take higher powers of square matrices. And this means that you could take a polynomial of a matrix. And it turns out that when you do this, the transformation that's applied to the eigenvalues is just the polynomial. So if we have distinct eigenvalues, we have all of them being a multiplicity 1. Well, if we represent the matrix in terms of its eigenbasis, because they're distinct, we can do that. So we represent A as a diagonal matrix in the eigenbasis. And then if we apply a polynomial to the matrix as a whole, because we have this nice diagonal form, all the higher powers of a diagonal matrix are just higher powers of the elements. So this matrix squared would just be lambda 1 squared here, lambda 2 squared here, and so on, because it's diagonal. And any linear combination of these is certainly going to distribute into the entries in the matrix. So really, this polynomial is just going to come inside and get applied to each of the entries. And these entries along the diagonal of the matrix are certainly going to be the eigenvalues of the matrix. And if we want to talk about this in the canonical basis rather than an eigenbasis, we can just apply a change of basis matrix, make this argument after that change of basis, and then move back out, move back from the eigenbasis to the canonical basis. And when the eigenvalues are not distinct, like we said before, it's not a formal argument, but because the set of matrices with distinct eigenvalues is dense in the set of matrices in general, that is, for any matrix with non-distinct eigenvalues, there's a matrix very, very close to it that does have distinct eigenvalues. Because of that, we can make a continuity argument. We can use an analysis kind of argument with limits to say that, well, if this is true in the case where eigenvalues are distinct, well, that's by far the most common case. And if they're not distinct, we can nudge it a little bit such that they are. And then nudging back can't change the eigenvalues so much. So that's kind of a heuristic limiting argument as to why this spectrum mapping theorem is true, regardless of whether the eigenvalues are distinct. Are there any questions about that? All right, so we'll move on to our last topic, which is the Cayley-Hamilton theorem. And so the point of the Cayley-Hamilton theorem is that we've said we can apply polynomials to matrices. And we saw before that each matrix has an associated polynomial, which tells you something about the eigenvalues of the matrix. And so if we plug a matrix into its characteristic polynomial, it kind of feels very neat, very nice that it would be a root of that characteristic polynomial. And I'm not going to prove this, but I am going to show an example of this. This here should be the zero matrix, I believe. So we're going to say A and B are 2 by 2 matrices, and we're going to specify that their determinant is 1. And this TR here is the trace of a matrix. So the trace of a matrix is the sum of the elements on the diagonal. The trace of the n by n identity matrix, for example, is just n. So if we think about the characteristic polynomial of B, which is what we're going to need if we're going to apply this Cayley-Hamilton theorem, let's expand this out. We're going to have this 2 by 2 matrix, and on each of the diagonal entries, we're going to have lambda minus that. And these here should be negative entries. And if we just expand this out using the 2 by 2 determinant formula that we already know, well, this is going to be this here times this here. So the first minus the fourth, the first times the fourth, sorry. And we're going to subtract this one times this one, which is going to mean that we end up with the product of these two minus the product of these two. And so if we just expand out, well, we're going to have a lambda squared, certainly. And we're going to have lambda times b11, lambda times b22. So we're going to subtract that. And B11 plus B22 is the first entry of the B matrix, and the fourth entry of the B matrix, which is just the sum of the diagonals, which is the trace of B. And also, if we so we're also going to have B11 times B22. And if we take this in conjunction with the B11 times B22 positive minus B12 B21, well, this is the ordinary diagonal of the matrix minus the other diagonal. For 2 by 2 matrix, that's just the determinant. So we have lambda squared minus the trace of B times lambda plus the determinant of B, which we know is 1 by definition. So we know this is the characteristic polynomial of the matrix. That should be lambda. And if we continue with this, we'll apply the Cayley-Hamilton theorem here. We'll plug B into this characteristic polynomial, and we know that the characteristic polynomial of B evaluated on B is going to be the zero matrix. And rather than a 1 here, we interpret this as the identity matrix. Now we can just change this up a little bit to get it closer to this equation here. Again, this is the zero matrix. If we multiply by AB inverse here, that's just AB. AB inverse here, the B inverse and the B are going to cancel. We're just going to have A. And this is just a scalar. And here, that's the identity matrix. So this is just going to come into there. And on this side, it's still 0. And now if we take the trace of both sides, we're going to have the trace of AB minus the trace of B scalar times the trace of A. And the trace is a linear function, certainly. So that's going to distribute. This scalar is going to come out of the trace. And we also have just the trace of this term here. And the trace of the zero matrix is just 0. So this equation here is satisfied. The trace of AB minus the trace of A times the trace of B plus the trace of AB inverse is just 0. So that's actually all the content we have for today. But we'll move on over to Discord. I'll post a link for the Discord in the chat. And I'll also post the problem set. The other thing that it would be great if you could do is fill out this feedback form on the workshop. And this is just going to tell us what kind of content and style you would prefer for next term. I'm not sure whether that will be online or in person. We'll have to see. But so that's the feedback form. And this is the invite to our Discord server, where you can hop onto one of the problem discussion channels and talk about the problems. And the problem set for this week is here. Thank you everybody for coming. If you haven't filled out the attendance form yet, that would also be good. And this is our last workshop for this term. But we will have more next term.